Plate bending actually it is like the beam problem, but the beam is 1D. 1D in the sense that the domain is 1D. Domain of the beam. For the plate bending, it is a 2D problem. 2D problem, the domain, your domain is 2D as well. If you consider only the plate bending problem without any in-plane deformation, that's pure the plate bending. If you also incorporate the in-plane deformation, that means you are combining the plate element and the plane problem. It will be the plane stress, of course, because in order to be a plate, it shall be somehow thin. It cannot be like the plane strain case that you have infinitely long, infinitely thick element that will not form the plate behavior. So if you combine the plate bending to the plane problem, which is a plane stress. Sometimes people call this one membrane. Okay. Anyway, you will be getting the shell element that incorporate all bending and in-plane behavior. So the degree of freedom for the plate bending will be mainly the out of plane direction. Out of plane displacement, or out of plane displacement, we should call it that way. This is in plane. Displacement. So when you integrate these things, then you have 3 displacement degree of freedom, and then we will come across the rotational degree of freedom as well. So now I will show you how we formulate the plate bending problem. So we will start with the one element, structural element. Like this. I think I need to give you a little bit more background. I'll be back to the above. That part is about the plate bending. The fact is there are 2 kinds of formulation. 2 kinds of formulation includes the thin plate formulation and thick plate. Thick plate is Mindlin Reisner plate bending formulation. Well, if you want to make an analogy, the thick plate is associated with the Timoshenko beam. Timoshenko beam account for the shear deformation. For the plate, Mindlin plate is incorporating the shear deformation as a component for the use of the deformation calculations. So with this, it behaves better than the thin plate. Thin plate is a Kirchhoff plate bending problem. I decided to omit the thin plate bending because I believe that this thick plate formulation is actually easier to use and more useful to do. So we don't spend time in that thin plate. If you want, I can just share the material, but when it comes to the finite element formulations, the thick plate turns out to be quite straightforward. And I think one thing I would like to emphasize is that when you think of the deep beam or thick plate, and we learn so far, we try Timoshenko beam, we are developing, we are working on this Mindlin plate bending problem, and we have perception. I think we have perception that the element like this is going to be capturing everything. I mean everything in the sense of the deformation of the deep or the thick structural member. But if possible, you should use the continuum element, such as the plane element, shell element, or the 3D brick element for the analysis of the thick structure like this. For example, like the foundation, a pie cap. Why? Even though the plate bending or the Timoshenko beam accounts for the shear deformation, but still that shear deformation is caused by the behavior of the beam shear. You got to think all the way back, and you can see that there are many assumptions about the beam has been posted there. The strain distribution is actually coming from the beam or the behavior under flexures, and then the shear component was later on incorporated. But that shear deformation, the pattern of the shear is not the same as the case where you have the structure of which the thickness is very large, like the pie cap. I mean, I would like to emphasize this fact here because you will not, I do not want you to overuse or have too good impression with the element that can account for the shear deformation, and then you think that, oh, I might not really have to use the continuum element because this Timoshenko beam and thick plate will be accounting for the behavior that comes from the very thick structure. So we can see it here. If we talk about the pie cap foundation, okay, you have the pie cap, you have the column. Basically, the behavior of this system is more like a strut and tie. So strut and tie has nothing to do with the flexures. So we have strut and tie model forms. You have steel tie. You have the compression strut from concrete. And you do not have the bending like we derive in Timoshenko beam. You have two sides of the beam with the given rotations. So these are used to calculate along with the cross-sectional rigidity of the beam EI. You can get the moment, and then the shear deformation was computed accordingly. You use the reduced integration in order to evaluate the shear part of Timoshenko beam to avoid the shear locking, and so on and so forth. But all of these things we used to talk about are under the formulation of the structural member like this, which is the beam. Okay, so it is useful, but you do not extend into the cases where that formulation might not pick up the behavior as well as the 3D elasticity. So 2D continuum elements or the 3D elements will work out better. And the case like this, if you evaluate the design, in general, in the design office, you will use either strut and tie. Some office use a strut and tie as well. But strut and tie, you need to set up some sort of the size of the strut, and you need to determine many parameters. Mostly people don't go for the elasticity using the continuum and run the full-fledged finite element analysis. So the Timoshenko beam was used, the thick plate was also used for the design of the foundation. If it is just F2 foundation, then just the beam element like Timoshenko beam might be used. I can see some design office use these techniques. Even in the review of the foundation of the expressway construction, the big construction projects, the foundation, the pie cap was made from was modeled using the thick plate. Okay. The point is that to do so, it will be conservative, because the behavior, actually the load transfer is better through the strut and tie. Strut and tie gives you better stiffness, and the load carrying mechanism is not as brutal as the plate bending. So the use of the strut, in reality, it's gonna make your design conservative, because you design based on the theory of the flexures, but in reality the real behavior is in this mode rather than the flexure mode. So your design will be automatically conservative. The steel required in the design like this will be more than the strut and tie model design in general. Okay. So this is widely used in several programs for the foundation design. But sometimes if you really want to check what's going on in the foundation, especially when you are dealing with the case that is very important, you might need to come back to the finite element analysis for the continuum element in order to get the actual behavior of the load transfer mechanism in your foundation, in your pie cap or thick element. Like for the transfer girder, well, that depends as well, but it is not as brutal as the pie cap, because pie cap is very thick, and we generally expect the stiffness very high stiffness from the pi cap. So the conservative design approach using the bending element determine the force, internal force required to provide the capacity of the cross section from the flexures is going to give you quite a big room for the safety margin. I just came across the question from Dustin. Sir, just have a couple of clarification for homework. For the spurious mode of single element, is it okay to assume E equals to 100 and Poisson ratio equals to 0.2? Yes. I actually want you to go to use these two numbers. Number 2, for the spurious modes of combined elements, do we need to show all deflected shape? It is something more. I know that's a lot. So you will not need to. First of all, you will see the what is it? You will see the eigen values associated with the eigenvector. So maybe you pick up the cases, first 5 cases, of which the lowest eigen, that is corresponding to the lowest eigenvalues. Okay, so 5 cases, 5 modes enough, corresponding to the smallest eigenvalues. Okay, right. Now we come back to the elements of our interest for today. We have this. Next week is not the holiday, right? Because it is sort of official that the Thai government does not allow us to have the holiday during this Songkran festival. So we are going to have class. Initially, I kind of thought that we can have like a short break from the class, and I was so happy. But we're not gonna have that. Yeah, just remember. Okay. Today is a low energy day. You can find my. I think it will be fun to me to just go through many teachings and then see how lively my voice is for each class. Sometimes it is overly lively, like yesterday. I don't know why do I have that much energy for yesterday. I don't have much for today. You might prefer the class with low energy mode, because with the high energy mode, that's gonna be a very fast talking, and it might be difficult to catch. So it might be at the speed of light. Okay. So I'll explain you what's all of this. I'm quite sick of being locked down. To stay home continuously for these many days. Okay. So don't worry, I'm gonna share the note as usual. Oops. I think all the class notes are uploaded quite almost real time. Every class it will be no more than 2 days delay. If any is missing, let me know. Okay, the coordinates is then established. We are considering a piece of plate, an infinitesimal piece of plate. So we took this from the big plate domain, and the x-axis is established, y-axis, and the z-axis, z-axis. Okay, so right hand rule goes like this: x and y and z is going as your thumb goes up, right hand. I'm start drinking coffee right now, so I hope that it's gonna kick in probably in 20 minutes. I'm gonna drink a lot now. All right. Then we also define the displacement along the x-axis. We make it u. We call it u, and v, and for z is going to be w. You might wonder, I talk about plate bending, and right now we are talking about thick plate. I'm not going to incorporate the plane problem in this one here yet, but you might wonder why is the u and v are in here, and u and v are in here for the reason that the u and v will be like not the displacement at the centroid or center of the thickness through the x and the y. No, it is caused by the bending behavior, pretty much like this. So you can have the u, this point can displace, this point can displace like that. But if you consider at the neutral axis, neutral layer, neutral plane of the plate, you will not have the displacement in plane, in plane direction. Okay, so u and v that we are talking about now are the u and v that are varying along the z direction, but not the u and v at the plane, the neutral plane. Okay, and now we are going to identify the nodal points. So as we are considering one element like this, so we discretize, we come up with the structural elements, and at each point you expect the 3 degrees of freedom in the following. So the first 2 are the rotational degree of freedom, and the last one is the degree of freedom for the translation. So I just going to copy this. And I'm gonna get all of this and test it at every single degree of freedom. Okay, and that's it. So the node numbering will be following the system we used to have before. Node number 1, 2, 3, 4 will be going in the counterclockwise direction. So 1, 2, 3, 4, and circle it. Okay. Yeah. Each of them, and we're gonna call the degree of freedom in the following: W1, W2, W3, and W4. Okay. And then the rotation, how we call the rotation. This rotation, you can see the arrows here. This is the double head arrow, which stands for the rotation. The arrow is pointing towards the positive X and positive Y direction. And then you have this one is then called theta x1. Likewise for this one here, theta y1, and then theta x2, theta y2, theta x3, theta y3, theta x4, theta y4. Okay, so the in-plane displacement U and V can be expressed in terms of rotation. Rotations, we have many rotations, theta x and theta y. And the z coordinates. So U, let's take a look. If we want the displacement along the U, we're gonna need the theta y, right? The point is that theta y is producing the rotation like this. I'm not sure if you think of your right hand and point your thumbs to that direction. So this is the rotation. This rotation is going to make this top surface go to the positive and the bottom surface go to the negative x direction. Okay, so the u is equals to theta y multiplied by z. Z is at every okay, and just like this. So this is coming out I guess you can understand the graphic. This happen on like this side. If you imagine that it is happening on this side of the plate, and the displacement profile like this is going on. It is a 3D thing. I know it could be confusing. Next, the V is equals to let's take a look at the V. You can look at this one instead, so we don't just get congested in the same area. The V is the displacement along this direction, y direction, and as your right hand rule for the sigma x is going like this, that means this is going to happen, right? So the top face positive z is corresponding to the positive z, the values is going to the negative y direction, and the bottom is going to the positive one. And that's why you are going to need the negative sign. Next, W. W is given by W, which is a function of xy. That means it will be coming from the interpolation somehow, somewhere. Okay, so it is interpolated this way. And then we can look at the strain components we have from this problem. As the plate is very thin, then you will not have the component epsilon z. You have epsilon x first. Epsilon x come from partial derivative of u with respect to x, right? And then you know that the u is given just above, and it is the partial derivative of z times theta y with respect to the x. Now the z it has nothing to do with the x, right? They are orthogonal. Is the height z always a half of thickness? No. We are going to conduct the integral over the z direction. So the u we had in here is the u at any layer. So this is the thickness, and if assume that we are talking about u, we have the rotation theta y, right? So at this level of any z values, you have the corresponding u values calculated at that given point. So now we cos z it has nothing to do with the x. We can take the z outside, and then we just leave the partial derivative of theta y with respect to x out there. Okay, the first part. The second part, we are going to find the epsilon y, strain in the y direction, and that is the v with respect to y. And that is the partial derivative of minus z theta x with respect to y. Again, z has nothing to do with y, so you take the minus z partial theta x with respect to y. So the theta is varying, and theta will be approximate using the shape function later. W will be approximate by the shape function as well. So I might say that the theta x is also the function of x and y. Well, or it will be approximated. Now, of these will be approximated by the shape functions. To be approximated by shape functions. Now, come to the next page. Copy the date. Class. That means we have formally 5 more classes, but this semester we have like 2 hours class. Theoretically, you should have 45 hours class in total. Class hours in total, 45 hours, because we have 30 classes as it should be in the calendar, and 1.5 hours each, then 45 hours in total. That means just 2 days. Finite element, right? 2 days is 48 hours. So if I teach you finite element, and then I don't stop, I don't go for eat, I don't sleep for 2 days, then we can finish up this course. But we had so far up to the class number 25, and each class we have 2 hours. So right now we passes the 50 hours, and sometimes we have more than 2 hours. So okay, let's keep it at the bottom line, 2 hours. Then we are at 50 hours already. You have like a free 5 hours already. We're gonna have maybe 5 more classes. That's gonna make 10 more. Okay, so you get like a big surplus of 15 hours free. So that is the extra part you get from your tuition fee. Next, gamma xy. Gamma xy is the partial derivative of u with respect to y plus partial derivative of v with respect to x. So we combine all of these. Partial u with y plus partial v with X. And then gamma X Z. This is the shear. XY is the distortion in this plane, in the XY plane. And if we talk about XZ is along this plane. So you could have the distortion within this plane here. Okay, so what has to be done? You need the partial derivative of U with Z plus partial derivative of W with X. U with Z, U is the Z theta Y. Oops, no. Plus the W. W is going to be approximate using shear function anyway, partial with respect to X. The piece here for the partial derivative, this one, let me ask, the theta Y, is it changing along the Z direction? The theta Y come here. That means, is it changing along the Z direction as you move up or down along the Z direction? Theta Y is not changing. Theta Y is associated with the X and Y coordinates, because when you work on the beam problem or the plate bending problem, you are working at the neutral axis level, axis of the beam level, or the neutral plane of the plate level. That is where we associate everything with, and we are not going to have the variation of theta Y along the Z. So we can write this down as the theta Y, since the Z, partial derivative of Z is taken out. And move on to the partial YZ. It's going to be partial of V with Z plus partial W with Y. And V is the minus Z theta X to Z plus W with Y. You end up with minus theta X plus partial derivative of W with respect to Y. And then if we want to compute stress, so we have sigma X, sigma Y, and tau XY. All these stresses are in plane, and they are associated with the bending part. Should I just explain out there a little bit? In plane, stress can be determined from strain. For calculations of the flexural resistance. So we talk about sigma x, sigma y, and tau xy. And since I told you since we are dealing with plate, and the nature of plate is supposed to be thin, it is not going to be infinitely thick. It will not be the plate. So the rigidity matrix to be used for this problem, we are adopting the plane stress condition rigidity matrix, and here it is. Poisson ratio 1, 0, 0, 0, 0, and 1 minus nu over 2. And you be multiplying this with your strain, and the strain is going to be epsilon x, epsilon y, gamma xy, and that I will just substitute the values of epsilon x, epsilon y, gamma xy by the number we had from above. Copy this. Gamma xy, the whole thing, and then we expand, we just multiply, and we rewrite each of them in the following. Sigma x is equal to the E. We take the common factor this out there, and you don't have anything in this column. You're gonna have the Z as the common factor, so we take the common factor Z, and okay, this is taken out, and the rest will be, first of all, 1 multiplied by partial derivative of theta y with x, right? And then minus Poisson ratio times partial derivative of theta x with y, and that's it. First one. Second one, I go to the sigma y, so it is sigma y equals to likewise Ez, and you have the partial derivative of x, but it is a minus partial derivative of x to y plus Poisson ratio times partial derivative of theta y with respect to x, and that's it. The next part here, is the torque. XY has to be the this part to this part. You end up with the G, the shear modulus. The 1 minus nu is gonna cross out with 1 minus nu times 1 plus nu. Then you're gonna get the 1 plus nu multiplied by 2 as a denominator. That's the shear. So you have the shear and multiply by you have the Z and Z. Okay, so they are both common factor, and Z wouldn't supposed to be vary with the Y. In fact, I should have brought it out. Okay, so yeah. So the Z is taken out here, and then you have partial derivative of which one is plus, which one is Y with respect to Y, minus partial derivative of theta x with respect to x. We will compute the moment next. We have all stress components. Now we can compute the moment. Actually, why do we compute the moment? Okay, let me ask you. Ultimately, the formulation we have is gonna be the integration over the volume of the we are conduct all of this based on the principle of virtual work, right? So we will have the strain and stress, and then integration over the volume, so you can get the work done by the strain. So the B transpose the B thing, okay, you're gonna have the U outside the virtual displacement is going to be cancelled out at the force term, integration of the force over there. Anyway, we ultimately we end up with the B transpose dB that actually reflects what's going on inside your element. It will integrate every single part of the volume of your structure, and the integration there is the integration in order to find the work done by strain. Okay, so we are going to formulate the following. We try to look up for the moment, but the moment is actually the integration of the effects which is going on over the depth. There is the variation. Yeah. You have the variation of strain, you have variation of stress. So when you calculate moment, you take all of this into your consideration. So let's move next to the moment calculation. In order to find moment, you have moment, the three kinds of moment here. You have the mx, you have the my, moment about the y-axis, and mxy, and that is equals to, we got to integrate as the variation is occurring over the direction z. So from the half thickness at the bottom to the half thickness at the top, like this. And then we multiply by z. Z tell us the location. So as the strain and stress vary with the Z, you need to incorporate the Z, right? Z values. And that also, the Z also serve as like a moment arm. So if you have this one is DC, and the value here is your stress. Okay, so you have stress multiplied by DC. Turns out to be DC is not the area, it is the thickness. The moment you are going to get here is the moment per unit length, the M we just wrote on the left side here. So as it is per unit length, then we don't need to get the width, because we are talking about the plate, and the plate is like infinitely, we cannot define, right, which part is the width of the plate. So when we analyze, we get the moment per unit length, and then you can provide the reinforcement. If you analyze and then you get the magnitude of moment per unit length, then you can provide the corresponding reinforcement to be enough, and so on and so forth. So you have moment arm multiplied by stress multiplied by the thickness, then you get the force per unit length. Force per unit length multiplied by the Z, which is the moment arm, you get the moment per unit length. Okay, so turns out that we have sigma x, sigma y, and tau xy. And then the Z. So we conduct this integration. We are going to get rid of the issue about the Z. And we will worry about other things later on. So we're gonna expand this. So the integral here has to be repeated, and I'm gonna get the information obtained from this page. So why did I expand it out? It is not useful at all. There's no point to expand it. What? Okay, a little bit too large, but I still can manage. So first part, this one here. This one here, we have this Z, the Z. So you gotta plot this along, and then the whole thing there is getting in. And next part is here. Since you have the common factor Z, I'm gonna put it here. Likewise for this. Part down here. Okay. this. We have a minus sign, right? Yes, minus sign. So this is going to be minus. Just like this. For last class of the week, which means it is good for my throat, and the set. It is very well packed, and we conduct the integration. The integration does not bother these people in here. It just does something with the z square. So the c square part will be integrated, turns out to be c cubed, and when you have c cubed, you evaluate from minus t over 2 to t over 2. From minus t over 2, when you cube it up, you get t cubed over 8, right? 2 cubed is 8. So you get t cubed over 8 minus t cubed over 8. That turns out to be t cubed over 4. And t cubed over 4, you integrate the c square to c cubed, then you're going to have 3 as the denominator. So t cubed over 4 and 4 multiplied by 3, then you get t cubed over 12. Okay. So we have the e t cubed, make it clear, cube over 12, 1 minus new square. And I'll copy this to save the time. And yeah, the top part here is not changing, it's still there. And the thing is the this part here is the D matrix, but for the bending, rigidity, plate rigidity, rigidity matrix for bending part. Okay, well, if we have seen that the bending part is there, then the shear part is going to be coming, right? So let's the thing is, okay, you have the rigidity matrix. This part on the back here is producing something which is pretty much like curvature. นะ This is the derivative of rotation with respect to the dx. So rotation change, the rate of change of rotation with respect to the x and y coordinates. That implies the curvature. Alright. So the point is that the matrix here is going to be used for the we're gonna make the relationship of this matrix as the combination of the B matrix and the nodal point displacement or rotations. So I'm gonna pick this one up. Paste it here. And we are going to open it up, the gift box. We have the displacement vector being the W1 theta x1 theta y1 W2 theta x2 theta y2 and so on to W4 theta x1 theta x4 theta y4. And we make the B matrix, which is a strain displacement relationship or rotation, not necessary to be just displacement. So partial derivative of y with respect to x, you start first with what? W. It has nothing to do with W. You need theta y with respect to x. So you start from 0 and 0 and partial derivative of v1 with respect to x. My when 3 minutes, my equals to minus d theta x okay, you mean this, right? I missed it. Okay, thank you, Sivaram. Good job. Okay, thank you. And the next one, this is going to be 0 minus partial derivative of theta x with respect to y and 0. And the last one, 0 theta y with respect to y minus x with respect to x okay. Shrink it down a little bit. So these 3 columns are associated with the 3 degree of freedom for the node number 1. And then we just repeat the cell like this for the sets of degree of freedom for number 2. So you change to number 2. This one here, in fact, if you will need to do the final examination, why did I erase that? If you have to do the final examination, maybe this is a good thing to get you to do, because you have seen how the coding in the plane problem was carried out. So it is possible for you to make the code for the plane, for the plate bending by yourself, right? Is it going to be difficult? I tell you, this is super easy to do. It's gonna take me less than half an hour to fix all of this and change from the plane problem into the plate bending problem. So it will just work as easy as within just 30 minutes. So the infrastructure we had, the infrastructure that we already have constructed for the 2D problem, and we have the shape functions, we have derivative of shape functions. Everything was already there provided. So your life is actually very easy to just move from one point here to the next achievement, which is the just change from the plane to the plate problem. Partial derivative of y with respect to x, let me emphasize, is equals to theta y theta y I, and then shape function I. This is actually theta y only, okay? Theta y is approximated by nodal point theta y multiplied by the shape function. Okay, so if you take derivative, and first of all you will need to have the summation from I equals to 1 to n to element type we had Q4, Q8, right, Q9, and we take the derivative of this with respect to x, and that is it. That's why we come up with the things above. So we distribute the partial derivative in there. That makes the theta y1 partial derivative of v1 with respect to x plus theta y2 partial derivative of v2 with x plus theta yn partial derivative of shape function n with x. And we pull this out to here, right? To here, to somewhere like this, leaving only in the B matrix. Now, this part here, Is it going to be a problem? No, because you have the subroutine. We developed it from plane code plane stress, plane strain code. So this is easy. You just evaluate everything at the C and eta value at the integration points, and these are going to come out from your code. I uploaded and gave it to you. And likewise for this, okay, with respect to x, with respect to y, it doesn't really matter. You just distribute all these number to the right place in the B matrix. So the B matrix size is going to be how many rows? 3 rows. But how many columns? Element type multiplied by 3. So this is the size of your B matrix. It just gets bigger than before. Before it used to be 3 rows by element types multiplied by 2. Now it turns out to be multiplying by 3. And that is all. Okay. So the B matrix for the bending is established. We will move next to the B matrix, to the calculation for the shear part. So, oops. Shear deformation. Let's take the contribution from shear. You have tau xz and tau yz. These two are relating to the shear mechanism. So we need to again express the shear stress in terms of rigidity and the nodal point, rigidity and the strain. So and the strain part is going to be broken down into the B matrix and the nodal point displacement. Okay. So the cross section, if we consider per 1 unit length, when we consider the plate bending problem per 1 unit length, the cross section is going to look like the rectangular shape cross section. And rectangular shape cross section, when you incorporate the effects of the shear, you know that the shear distribution over the cross section is parabolic, and then you're gonna need the K factor, the shear correction factor K, which is 5/6, to just change from parabolic shape into the uniform shear distribution like this, because we cannot afford to have the precise shear deformation like it is in the real problem. So that thing is in your strength of material course long time ago. So shear correction factor times the G and times the thickness. This is the rigidity. The K is the shear correction factor. G is the shear modulus. T is the thickness. If it is the beam, then T turns out to be the area, because you have the finite area for the beam. But here, as it is going to be done over 1 unit length, then it is just the thickness. You do not have the length, so it is simply just the T. So K, G, T, and then multiply by the shear strain. And let's take a look at the shear strain. We have shear stress here. Shear strain is just up there. And you can guess what is going to be done. So the shear strain will be expressed in terms of the strain displacement relationships with the nodal point displacement, right? So this part is broken down, same old. Yeah, can keep the KGT, which is 5/6. G and thickness, and this will be broken down. So we'll see. You have theta y and you have w. The w will contribute to partial derivative of phi1 with x. Another one, partial derivative of phi1 with y. Okay. Next, theta x has nothing to do for this line. Theta x has something to do for this line, so you drop the minus phi1, because theta x is approximate by theta x1 times phi1 plus theta x2 times phi2, and so on so forth. Thus phi1 is coming in. That means for this guy here, phi1 is going to be plugged in, and here is going to be 0. And we repeat. So repeating this by copying this and paste. So 1 has to be changed to 2. So this will repeat until it gets to the last node, and you know it's gonna be this vector of W theta x1 theta y1 W2 theta x2 theta y2 like this, repeating. And here is your B matrix for the shear. What did I say there? B shear. It does not need to be all uppercase. And then K is going to be combining two parts. The first part, integration of the B bending, transpose D for bending and the B for bending, dx dy. Next part for shear. All these two are going to be numerically integrated. And that's it. So you can use the construction before, adjust a little bit. You need to come up with the D matrix for bending and for shear. You need to come up with the different B matrix, but that's just the different arrangement of the entries inside the B matrix. And then numerical integration facility is already provided, so it's nothing new. And you're done. So it is 9:40. Shall we? 20 minutes. Yeah. It might be possible to make the code for the plate bending, because we still have time. So let me switch to the desktop here. I'm gonna make a new folder. Plate. And I'll copy copy things from the plane. I take the rect mesh because we got a mesh. Shape function, this one, yeah, it could be used. Yes, it can be used to find out the mx, my, the moment per unit length. Main update, we're gonna use this one. Evaluation is needed. Gauss point, input read, that's gonna be needed. And I can copy and plate. Is that possible? Copy to the clipboard and then, well, edit, paste. It's not working in here. So I can copy from eval Gauss input read, main update, rect mesh Q shape, copy and paste it in the plate. No, I'm not asking Siri anything. Why? Quit, please. I didn't get that. You're not going to get that. I'm not asking you. There it is. So what it takes to make it the plate bending problem. Input file. Well, we can come back to this part later. C eta, we still need it. Let me check the. Okay, you can see everything. C eta, we are going to need it now. Is reduced integration. We can keep it there. Cases, of course, is going to be modified for the plate. So 2 turns out to be how many? 3. You have 3 degrees of freedom at each node. So 3 by 3. F6 is going to be 3 n node by 1. So loop over elements, the same thing. Rigidity metrics. For this case, well, we are going to need the 2D mat. Rigidity metrics for shear and rigidity metrics for bending. Actually, for a shear, it doesn't need to be. It is the K, which is 5/6. 5/6. What is that number? 5 divided by 6. Wow. 5 divided by 6 is 0.8333. Okay. I will put 0.83333333. Does not need to be in the bracket. And multiply by the kgt. I think we need the thickness, right? thk. So that is the thk. pthk stands for plate thickness. Make it pthk there. Right, plate thickness, pthk, and multiply by what else? You are getting this from here. 5/6 is in there. 5/6, then your thickness, then you're gonna need the shear modulus. The shear modulus can be computed very easily. Now see, should shear modulus, G is equal to E property of the I elements number 1. This is the E divided by 2 times 1 plus nu, which is E PRP of I comma 2 Poisson ratio, and that's it. And this is the G. Or I can just make it the MMY such that it will be replaced later. So this is the rigidity matrix. For this case, it is just the scalar values. For the shear part, for the bending part is already there. Elastic modulus, or it will be here, by the way. I didn't put it here. So PRTO EMOD. Okay. Rigidity metrics for plate. Mindlin plate. Elastic modulus, and then this part is shear part, shear rigidity going on, and then bending rigidity, and your DMAT B. These things are not going to be used. Probably, right? But make it this way. Rigidity matrix is going to be scaled by this thing outside. We make this one first, and then we say that DMAT B is equal to DMAT B multiplied by this, okay, to avoid a long expression. So I'll come back here. This is replaced by 1. This is Poisson ratio for number 2. 2, 1 is equal to 1, 2 is equals to 1, 1 for the 2, 2, and the last one is the 1 minus Poisson ratio divided by 2, or in other words, it is 0.5 multiplied by 1 minus Poisson ratio, and ultimately DMAT B is equal to DMAT B multiplied by the scalar value of E mod times the plate thickness cube. So PTHK, and as it is cube, then okay, divide by 1 minus nu square 12, so 12 times you can see here E mod P thick multiply 3 times divide by 12 minus 12 Poisson ratio square. E mod thick cube 12 minus 12 Poisson ratio square. So rigidity matrix is ready. Now we talk about the KELE, which is supposed to be adjusted to be accommodating 3 degrees of freedom, and EXYZ element XY coordinate it doesn't change because XY coordinate is still XY. You don't have more than that. So keep going. For J equals to 1 to element type, okay, this is just to transfer the XY coordinate. Now the reduced integration issue. The reduced integration actually can be conducted, but it will be on the shear part only, right? So we will do the actually the old code we can put the if for the shear part only in the old code. Yeah, it could be done this way, but it could be generalized. So we break the B matrix into the volumetric and deviatoric part as a default, and then we operation is just longer. Fine. Anyway, full integration first. So for K you get the C and eta. C eta, all of these will be the same, and then the B matrix is gonna be 3 by 3 times, and you have the B matrix for bending and the B matrix for shear, so got to separate them. B mat S, that is going to be 2, so B matrix for shear for bending, separate. And for I equals 1 to element type, which is okay, we're gonna get rid of all of these. B mat bending first. For the B mat bending, let's come back and take a look to here. B mat bending is in here. So 0, 0 for the row number 1, and that is 3 multiplied by L. You don't need to minus anything. It is equals to partial derivative of shape function with respect to x. So it is the derivative of shape function with respect to c times derivative of and that's gonna be plus as well. So this one is useful. Okay, so d phi dc times dc dx plus d phi d eta, this is the comma 2, so that means d phi d eta times d eta dx, right? Turns out to be dn dx, or the derivative of shape function with x. Next, move forward to, oh sorry, I didn't change the screen here. What I just did is here. So the 1 and the column number 3 times the L turns out to be d phi dx. Okay, and then come back. So this is the column 3L minus 2 is 0, 3L minus 1 is non-zero, and 3L is 0. So I move back here. B matrix for bending for the row number 2, column 3 times L minus 1, okay, equals to, this is the row number 2, this column, which is 3L minus 1, and derivative of phi 1 with y, phi 1 with y, phi 1 with y in here, phi 1 with y. This is dn dx. We need dn dy, right? Which is here. Okay, so this is d phi dy. Got it. And then the B mat, B, row number 3. Row number 3, column number 3 multiplied by L minus 1. Extra equal to, come back. We talk about this one, this row here. So this first column, 3L minus 2 is 0. You don't need to do anything. 3L minus 1, you get minus, oh, we gotta put the minus sign for the line above there. But anyway, we can get back to it. This one is minus partial of phi 1 with x, so with x and with y. Minus. First of all, just come fix this thing. Minus and minus. So this one is going to be what? X first, right? Minus x put a minus sign, put a minus sign, and remove this part here, and it is yeah, just this. This is the dn dx, right? Minus dn dx. Okay. Minus dn dx. And lastly, B mat B 3, 3 times L, no minus. It's going to be dn dy plus okay. This is the B matrix for bending. Let's do the B matrix for shear. So B mat S 1 comma let's go to the shear. What you have this first and second. You can see here now, you cannot only just evaluate the derivative. Before, in the plane code, we don't need this just shape function. We need only just derivative of shape function, but now we need the shape function itself also. So we need to evaluate the shape function at the C, I, and eta I as well. So we need to call the function for the shape functions evaluations as well. So let's get back. We over time right now. In here, the Q shape is given, and how to use it. Let's come back here. We have C and we have eta. Okay, JK whatever. That we call the derivative of shape function. Now we call the shape function, and we call it from C, from eta, and element type. Okay, it's going to be fine. Close the bracket. So N shape is called. N shape has to be in the dimension like this. So one column, many rows. Depends on element type we have. And what next? N shape. Okay, come back to this page. This one first. So 1, 3 times L minus 2 turns out to be this column number. 3 times L minus 1 has 0 here. 3 times L, it is the shape function. So 1 and 3 times L minus 2 is equal to the d phi dx. d phi dx is this one here. And beam at S of the same row, but 3 times L without minus equals to N shape of this is element L, the shape function L, column number 1. That's it. Okay, and the next row, beam at row number 2, column number 3 times L minus 2 is equal to partial derivative of shape function with respect to y. So we need the d and dy. And that's it. And beam at of 2, 3 times L minus 1 equals to 3 times L minus 1 is from here. This one. So it is the N shape of L comma 1 as well, negative, right? Minus, and that's it, done. So N4, this part here is going to loop for as many times as the number of nodes you have. Q4, you will loop this over 4 times, 8 node, 9 node, whatever. Then it's gonna perform the calculation like cell by cell. For example, this one for the shear part, so it finish this cell first, finish this up, move to the next cell and plug in, and then move to the next cell. So each cell corresponds to one nodal point. This is for another nodal point, and so on. Like the B matrix for the bending part, this cell, this sets associated, it is associated with the node number 1, and then this set for the node number 2, and on and on. Okay, so we finished the B matrix. The next part is going to be the we evaluate the B matrix one at a time already. I delete the part there because it is for the plane problem. So K element is equal to KELE plus B mat transpose. Now we need to B mat B transpose times D mat. I think D mat is also D mat D, right? D or D mat B and D mat S. D mat B, B mat B, Jacobian of transformation and weight. That is 62 lines already. KELE plus, then dot 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 N plus dot dot dot. We just write at the 60 lines, and then B mat S times D mat S times B mat S, and the Jacobian of transformation, weight and weight. If we don't do the reduced integration, then it's gonna be like this. Okay, that's it. Now we get the element stiffness matrix for the bending, plate bending. Oh, at the end, yeah. Close it down. So we get it. We can come down to the reduced integration part as well, but well, we better discretize the domain well. The discretization helps alleviate the issue. Line 73 and 79 side should be plus for the NDY. Okay, let me see. 73. Yeah. 73 and 79 plus. Thank you, Navinda. And 79. Okay, plus. Thank you. Yeah, this could be disastrous. if this slip through, it's gonna be difficult to find. So thank you so much for the input. Alright, so this is it. The rest of this work is going to be just the cleaning up. I think I'm gonna remove the features for the reduced integration, maybe for time being, to just get it to work first, and that could be furnished later. And the rest of the thing, we have to come to this part, the plugging in, because the plugging in previously one node accommodates 2 degree of freedom. Now one node accommodates 3 degree of freedom. So if you go with the nested loop from J from 1 to element type, from K1 to element type, what's inside here has to be the 9 entries, because you have 3 DOF in rows and 3 in columns. That makes the 9. So this thing in here shall be adjusted to 9, right? Okay, but anyway, we ran out of time. This is overtime already, almost 10:15. You're gonna go for earthquake engineering. So we will continue. We will clean up the code and we're gonna make it work. And we're gonna see the plate bendings, which is quite fascinating to you. And this can be used, yes, for the foundation analysis. If you want to use just the plate bending theory for the analysis, which is going to give you the conservative number anyway. So that could be done. Okay, you can use this one. Later on, we're gonna go for the 3D elasticity, but that is very expensive computation. So you might want to just stick with the cheaper one and make your design conservative. Anyway, right, we are done for today. We're gonna meet again on Monday, as Monday is not the holiday, so we're gonna meet. Have a good day, guys. Bye bye.